Okay, let's get started. So, I am going to do a few things out of order from what was presented on the class schedule. I will talk about the World Wide Web today. I will just wrap up the fault tolerance material and we will talk about the web, and then we will go to distributed systems. On the course schedule, we are distributed file systems rather. On the course schedule, we had the file system topic before the web. The web topic is relevant to the lab, so I thought I will do it earlier, so you get a little more time to digest that material and use it in the lab however you wish. So, just to recap, last time we were talking about fault tolerance, and specifically we talked about Byzantine fault tolerance, we talked about Paxos as a consensus protocol and so on. Okay, I have one more thing to discuss from that topic, and then we will switch gears, talk about the web. Okay. So, as I mentioned last time, Paxos as a protocol is hard to reason about. Okay. So, there are been multiple attempts to figure out and convince people how it works, and there are many variants of it. There are some who felt that maybe there should be a simpler protocol that is much easier to understand, which has resulted in many such ideas. One of them is called Raft, okay, which is also a consensus protocol, and their goal was to make sure it's understandable. So, in the paper they clearly spell it out, saying when we describe it, it should be clear why this works and it shouldn't be hard for you to reason about it. I will leave it to you to read the paper and figure out if their claim is true, whether it's any more understandable or not. It's certainly easier to reason about because it is not meant to do everything that maybe Paxos does. Okay. Paxos was you have to agree on an operation, and the operation could be anything. Okay. It could be the state of a lock, it could be the order in which you should apply queries, or it could be what is the output of a request. Okay. What is the response for a request that is being sent to a replicated server. Raft specifically is designed for a set of replicated servers that are all processing the same request. When a request comes in, you send a copy of that request to each replica, okay, and that replica is then going to execute that request and store the result. So, in our database replicated database example, you had to send the same query to both replicas in that banking database example, so that they are consistent. Okay. And when multiple requests come in, you want to order them and send them to the database in the same order, regardless of network latencies where they might not be received in that order at both the replicas. So, Raft is actually a very good use case for such scenarios. Okay. And it uses a concept called state machine replication, or SMR, which has become very popular in many distributed systems. Okay. Essentially, what state machine replication does is it's implemented as a log file at each replica, where the log is used to determine the order in which requests have come in. Okay. And you essentially get a total ordering that is agreed to by all parties, and you execute all the requests in that order. Okay. So, the basic idea is if you have two replicas that are exactly identical, okay, and each of them processes the same set of requests in the same order, at the end of all of those requests, they should still have the identical state, because they did exactly the same operations. Okay. So, each operation, if it is done in the same order, should move that replica from the same state to the next state that is also similar or identical to one another. Okay. In this way, you can ensure that replicas are consistent with one another, and that is the basic idea of state machine replication, where the replica is thought of as a state machine, where each request moves it from one state to another. And then if you, and it could be a database where a request is a query. Okay. So, your state of the database, you apply a query, maybe some records change, that is the new state of the database. You apply another query, it moves to yet another state. And the basic idea is if you do this in the same order at all the replicas, then they end up in the same end state as well, which requires, which is what you want for consistency. So, the way this notion is implemented, state machine replication, is through this notion of a replicated log. Okay. So, whenever requests come in, they are first stored in the log. Okay. Each server stores a log of commands and it executes them in order. And basically, when you have incoming requests, you have to put them into all the logs of all the servers and ensure that the requests are written to the log in the same order. Okay. So, if requests come A, B, C come in, okay, if one log says ABC, you don't want another log to say BCA, because the log is the order in which you are going to execute the request. So you want all the logs to reflect the same order regardless of how requests have come in. Okay. This is no different from what you actually are doing in your or you did in your lab 2, where you derived a total ordering of requests regardless of the order in which they came in. Okay. So you already implemented a very simple form of what is being done in SMR. Okay. In your case, you did not deal with failures and so on. In this case, it has to obviously deal with failures, which makes things more complicated. But that's the basic idea. Each incoming request is then replicated into the log, and then each server is going to take a request from the log and execute them in log order. And if the logs are identical because you ordered them using the consensus protocol, then I think you are going to end up with the same consistency. That's the basic idea. Okay. Now, Raft requires you to elect a leader, and then the leader is going to determine the order. So, this is not completely distributed. There's a leader that's going to send requests to the followers, and then basically there's a majority is going to vote and decide in what order to actually apply the request to the log, and then you commit those requests to the log. Okay. That's the basic idea. It's a voting based protocol. I'm not going to actually go into the protocol for reasons of time, but the basic idea is the leader is going to ask all the followers, saying, here are a set of requests, how should we order them? The requests are going to be voted on, and the majority will decide this is the order. And the reason it's a majority is you have to deal with failure. So, some small number of servers can fail, and yet you can continue to make progress in the protocol. Okay. That's the basic idea behind it. Okay. I just wanted to mention it here because it is considered as an alternative to doing something like Paxos, which can also do the same thing, okay, but it will use the more general protocol I talked about last time. Okay. Is that clear? I will have a pointer to a paper on Raft, and you should certainly look at it at a high level to see if you can understand what this concept is in more detail. Okay. These steps, which I obviously skipped over here. Okay. So, with that, I am going to switch gears, okay, and move on to the next topic, which is going to be on the web. Okay. I am going to start with some very basic principles of web, some of which you may already be familiar with, and then the rest of the class we are going to talk about web caching and content distribution. Okay. So, let us start with the basic client server request response protocol that the web uses. So, clearly the example here is one where you have a web browser that is basically communicating with the web server. You send requests using the HTTP protocol, you get responses that you can then display in your browser, and the request might require the web server to fetch a document from a file or a database or wherever the content is stored. Okay. Now, as far as the browsers are concerned, we won't go into the details here, but what this picture shows is all major components of a web browser. And you will see that there is a user interface component, there is the browser engine, there is a rendering engine which takes the HTML document and decides how to render it on a user screen. There is a part that does network communication. You might have things like scripts, JavaScripts or PHP scripts embedded in documents. So, your browser might actually need an interpreter to process that script and produce a response. There will have to be parsers to parse HTML or XML documents that are being sent to you from the server and so on. Okay. Now, we don't need to go into the details of this other than to understand that browsers are complicated applications. They have a lot of functionality built in, and this functionality might get replicated if you have things like tabs. Okay. Each tab will have to have a set of these components that are responsible for fetching documents and rendering them on the screen and so on. Okay. Now, as far as this rest of the lecture is concerned, we are not going to use just the request response client server architecture shown here. Rather, we are going to use a client proxy server architecture. Okay. The proxy is an entity that is going to sit between the client and the server. Okay. Here we have shown an FTP server, but in the case of the web, this is going to be an HTTP server, okay, but it does not matter what the proxy is for. The basic idea is the browser, rather than sending requests to the server, is going to send requests to the proxy. Okay. Now, the proxy has to then process that request. It could do so by either fetching or sending a request to the server itself, or if it has the requested content already stored locally, maybe in a cache, is going to reply with that document. Okay. So, the most common case of a proxy is for web caching. Okay. You have a cache of recently accessed web pages. Any user that's requesting web pages, you keep a copy of it in your local disk. When a new browser request comes in, you first see if that web page is already in your cache. Okay. If you get a cache hit, you can reply immediately. You don't need to go to the server at all. Okay. There's no server interaction in that case. You just reply with the rest with the content. If there's a cache miss, which means the web page is not stored in your cache, then you have to go to the server and fetch it. You keep a copy in the cache and you also send a copy to the server. Okay, so that's where you're updating the cache. So, in subsequent requests from maybe this user or other users can use that cached content. Okay. That's a common use case for a proxy, but proxies are used for many other scenarios as well. Okay. Another scenario proxy is used for is what is called transcoding. Okay. In transcoding, you are actively changing the content to make it more suitable for the user. Okay. So, maybe you are watching a video, but maybe you are watching it on your smartphone screen, which is a small display. Okay. If you are fetching a high resolution video from the server, okay, sending that high resolution video to the user is not very useful, because they only have a limited number of pixels on their screen to view that video. Okay, maybe it's HD quality video designed for a large screen, but you are viewing it on a small screen. Okay. So, what the browser proxy can do is it can transcode the video or convert it to a lower bit rate and re-encode it, so it is more suitable for a smaller screen. Okay. That is one example where you are actively processing the content. There are examples where you can take a web page that is designed for a desktop and dynamically convert it to a web page that is suitable for a mobile browser, okay, where you just change the layout. The content has not changed, but you change the layout so it looks better on a mobile device as opposed to it was designed for a larger screen. That is another example of transcoding. So, proxies can perform active processing, proxies can perform passive caching. Okay, so, there are many scenarios where you could use this. Okay. Here is an example proxy where it is doing protocol translation. Okay, this example, the reason there is a FTP server is the browser wants to fetch a fetch some content, okay, and it sent an HTTP request to the proxy. The proxy has converted that to an FTP request and fetched the content. So, you are converting HTTP request to equivalent FTP request. This is called protocol translation. Okay, you are changing a request from that was sent in one protocol and sending it using another protocol to the server. So, that is another example of what a proxy can do. Okay, so, many different use cases. Today, we are only going to talk later on about caching. Okay. So, here is an example of a Apache Web Server. I spoke about this briefly when we were talking about architectures in chapter 2 or chapter 3, when we talked about multi-tier architecture, servers and so on. Okay. So, again, the thing that you want to keep in mind is in the Apache Web Server, okay, it is a modular architecture. When you configure the web server, you configure a set of modules that will perform request processing. Okay. When a request comes in, okay, this is basically a request arrived here, it is going to go through a sequence of processing steps, okay, that is going to be performed by Apache. Okay, each of these steps invokes one or more modules or one or more functions within Apache that does some partial processing of the request, then the request is handed to the next stage. So, it is pipeline processing of the request as you go from the start to the end, and then you produce a response and send that back to the user. Okay. And these modules could do a variety of different things. If you have let us say encrypted request, if you have HTTPS request, there have to be modules to do encryption and decryption. Okay. If you written your web server code in PHP, Apache can have a PHP module that is going to do PHP processing in at the server end. Okay. So, there are many things that you could do, and if you have actually configured an Apache server, you will know in the config file you get dozens and dozens of modules. You configure the server and say which modules do you want to use for your website, and then whenever a request comes in, it will basically get processed by those set of modules. Okay. So, it is a modular architecture, and you will basically have pipeline request processing. Okay. Now, this does not mean that Apache by itself is multi-tier. Apache simply does HTTP processing. Okay. It is just that even for HTTP processing, you have to use a modular pipeline architecture. Okay, now if you have, sorry, what's your question?
Is there an example for that? I can get what exactly happens. Is there an example?
What is an example of pipeline processing? Okay, the question is what do you do when you have this pipeline processing? So let's say you sent an HTTPS request, which means you encrypted the connection. So the first stage here is to decrypt the request. You know what the request is because the request is fully encrypted. So you will basically do the decryption, okay? And then you extract the request, which is an HTTP GET request, say, and then you will basically get the web page from the disk, and then you have maybe the web page has some PHP commands. Okay, PHP is a script that's embedded in the web page. So then you have to run a PHP interpreter to actually then process that script and then produce some response and so on. So you will be, and then again at the end you might have to re-encrypt the response, not re-encrypt, encrypt the response and send it back. So you went through a sequence of steps. Okay. Now if this is a multi-tier application, some of these requests might actually require you to send that request off to another tier altogether. Okay. And that tier will produce a response and then send it back to HTTP and it will continue processing. Okay, which is what is shown here. Is this is your Apache Web Server in your multi-tier architecture. This could be any piece of code. It could be CGI, it could be written in Java, it could be written in Ruby on Rails or Python web frameworks, doesn't matter what the framework is, but that's your application server tier, and then you have the data tier or the database tier. Okay, so requests come in, okay, they go to the HTTP server or the Apache server, then they go to your app server, they possibly make a query, responses flow back the other way. Okay. Now in many cases, even at these multi-tiered architectures, you might employ caches, and there could be caches at multiple levels. Okay, so you might have a cache sitting here in your app server that has cached previous results of database queries. In this case, before making a query, you look in the cache to see have I already retrieved this request or retrieved data for this query. And if so, you just use the cache response rather than making a database query. Okay, so there are complex design decisions you have to make even when implementing a multi-tiered web application. Are you going to use caching? What are you going to use as far as the app server is concerned, database servers and so on? And do you do replication of the front-end servers and so on? Okay. So this is an example of clustered architecture, okay, where each of those boxes there is themselves a multi-tier architecture shown as one box, and they are replicated. And then here is your front-end the load balancing switch. Okay, so requests come in and you get sent to one of these, in this case 4 replicas. Each replica can perform multi-tier processing of the request, even though it only shows one. That could be a multi-tiered architecture, and then responses flow back through the load balancing switch. Okay. This is somewhat like what you may have implemented in your lab, okay, where you had a cluster and then you had a dispatcher. Okay. Here is another architecture for the same thing, where here is your client, that's a load balancing switch, okay, and there's a dispatcher there that is responsible for deciding which of those web servers is going to manage which set of clients. And so essentially when you come in, you are going to get mapped to one of these requests based on the dispatcher, and then from that point on, the load balancing switch in this case is simply going to forward to one of those servers depending on where the client has gotten mapped. Okay, next question.
Why is the dispatcher why is the dispatcher not dispatching?
Okay, question is why is the dispatcher not dispatching the messages? That's a good question. So there are many different architectures. So you could put the dispatcher and the load balancer in one entity. In that case, you are basically sending the request the dispatcher has mapped to, that's where you go. Okay. The specific example shown here is doing what is called session level dispatching, which means every user gets mapped once to one of the web server. And from that point on, all requests that are coming from that browser, from that point on get sent to the same web server without any subsequent need for dispatching. Okay. So if you are going to do request level dispatching, the dispatcher has to be in line with the request. It has to receive a request and make a dynamic decision. If you are doing session level dispatching, you do that one time for a request, not a request, user session, and then the switch can simply have a table saying client 1 go to server 2. So all requests from client 1 are sent. There is no intelligence there anymore.
Okay. Is the switch a bottleneck?
Okay, the question is, can the switch be a bottleneck? In this case, if you have a very high volume of requests, the switch could become a bottleneck. Okay, the switch is simply forwarding requests, and you could make that entity distributed as well. But if you're not doing much processing, these switches can, if implemented in hardware, can support very high request rates. Okay, so you can get specialized switches that have hardware support to do this at a very high volume. Okay, question?
So when the session begins, does the client first talk to the dispatcher?
Okay, the question is, when the session begins, do you talk to the dispatcher? Yes, if you actually see the steps here, which I had skipped, but I'll mention this. So you basically start a request. Step 1 is you basically go through a web server to a dispatcher. The dispatcher selects the server, okay, and then it informs the switch, and then from that point on, you are going to switch to simply forwarding. Okay, yes, so that's exactly what's happening. Okay, any other questions here? Okay, so here is some information about HTML and HTTP. Okay, so essentially HTTP responses essentially come as MIME encoded documents. Okay, just as when you send an attachment in your email, that attachment is encoded using a format called MIME, okay, which allows you to take any object and say this is the type of the object, and it has an ASCII version of that encoding, so it can be sent over a network. So you will see that you can HTTP responses and get you a plain text file, HTML file. It can get you images of various sorts. You can get a response as an audio object, video object. You can get a PDF document, an application. You can get mixed documents and so on. Okay. So these are all potential content fields of the HTTP responses. Okay. So when you request, send an HTTP request, in the response you could get any of these things. Okay. Could also get some status messages such as error or other things, but typically these kinds of web documents can be retrieved over HTTP. And here is essentially how HTTP works. Okay, this is the original HTTP 1.0 version of HTTP, where every time you make a HTTP request, your browser sets up a new TCP connection to the server. It fetches the document, and then the connection is shut down. Okay. If then you click on a link in that web page, you are going to make another connection to the same server. Okay. And then if you are going to fetch a document, if the document has 10 images, you are going to make 10 more connections to the server. Okay. Every HTTP request is essentially going to make a new fresh TCP connection and send the HTTP request over that TCP connection. Okay. Now clearly, as you can imagine, repeated requests from the same browser to the same server, okay, if you make new socket connections every time, is wasteful. So you have a variant of HTTP which is called persistent HTTP, which essentially uses a single connection and piggybacks requests. Okay, so you open one connection, and then you will send a request, you get a response. You don't shut the connection down. The browser actually keeps it open for some time, maybe anticipating the user might click on a link that sends another request to get more web pages from that server, and then you can use the same connection. It saves the TCP establishment overhead. Okay. So this is called persistent HTTP, also called HTTP 1.1. Okay, no question.
This has to be also enabled from the server side. Right?
This has to be enabled from the server side. Yes, if your server can support HTTP 1.1, which all servers do, then you can use this. So the first time when the browser sends a request, it will ask the server what version of HTTP do you want to use. Okay, and then you can go and use this. Yes.
These are a question regarding the dispatchers, the different types of dispatchers. How does the client browser detect the differentiation between the two types of dispatchers?
Okay, question is, how does the client browser differentiate between the two types of dispatcher? The client browser should not even know that there is a dispatcher. Okay, so all of this is what is behind the switch is completely transparent to the web browser. The web browser is simply going to see an IP address of the web server and send an HTTP request. So in this case, this entire clustered web server is going to advertise the IP address of the switch as the IP address of the server. Okay. So the client has simply made an HTTP connection to the switch, not even the real web server, sent it a request. Okay. Then it's the switch's job to figure out, has the dispatcher dispatched this session, which server should I send this request to, and so on and so forth. So, you do not, it is completely transparent. The fact that there are replicas as a dispatcher, none of that is known. Okay. Same is true in this case. The web client browser only interacts with this entity. The fact that there are 4 replicas behind that entity is not known. Okay. So, it is all transparent to the end user end browser. Okay. Any comment questions about HTTP 1.1? So, one of the design issues when you design a browser to use HTTP 1.1 is for how long should you keep your TCP connection open. Okay. User clicked on a link, got a web page from a web browser. Okay. Now, you have an active connection to that web server. Okay. You will keep it open because it is persistent HTTP, persist that connection, saying maybe the user is going to click on another link in that web page which will send another request. How long should the browser wait? Okay, if 5 minutes go by, should you shut it down? Should you take an hour? Okay, that is a design decision. Okay, typically, you cannot tell ahead of time because maybe it is a long document, the user is going to read it, and when they reach the end of that document, they may click on another link that goes to the same web server. Maybe it is a newspaper website. Okay, you are reading some long articles. Okay, so, if you say I will arbitrarily pick a short 1 minute interval and then shut the connection down, that may sometimes be inadequate. If you pick a longer interval, you are going to keep this connection alive. Okay. Now, maybe the user will go to another website. Should you shut the connection down? How do you know if the user goes to the back button, goes back to that website and clicks on the same link again or same web page again? You do not know ahead of time how the user is going to interact when they are browsing. Okay. So, you have to make a decision of how long you are going to keep this alive. The problem is even worse at the server end because the server also has to keep that connection alive. And the server is receiving requests from lots of users. Okay. So, you got a request from a browser, an hour has gone by, nothing has come from the user. Should you shut it down? In the meantime, maybe you are serviced lots of other users and you have lots of open socket connections. Okay. Each socket connection takes resources at the server. It takes some resources, memory state in the OS. It is going to keep adding additional state to the OS. Okay. So, sometimes there are policies in the HTTP servers where the server will shut it down, not the browser. The server will say, I will keep the connection alive for X minutes or X seconds, but typically minutes, and then after that, if there is no request, you won't persist that connection, unless the browser keeps sending keep alive messages that allow you to keep the persistent. But so, these are all design decisions to be made at the server, because if you are a busy or a heavily loaded server, popular server, you might have lots of open connections that are just sitting there idling, waiting for the next request to come. Okay. So, some of these things actually have an impact on how the resources get used at each server. Okay. Now, as far as whether you use 1.0 or 1.1 version of HTTP, the protocol, HTTP protocol is extremely simple. It has 5 commands. Okay. The simplest and the most common one of them is called the get command. So, the browser is supposed to return back to the user. Okay, process it and return back. So, that is the get request. Okay, you have the put request, which is not often used. It allows you to actually send a document to the server. Get gets a document, put allows you to put a document. Okay, that is typically not used unless the server has a specific kind of service called web dev. Otherwise, you do not send web pages to the web server, you typically retrieve web pages, but you can actually do that as far as the protocol is concerned. But what is more common is the post command. So, whenever you fill a web form and you hit submit, that request goes as a post request, not a get request, because now you are sending information to the server after filling a web form. Okay. You are not retrieving content, but you are sending information back. So, post allows you to send information back to the server. So, the two most common commands that you use in HTTP are get and post. Okay. You have delete and put. Delete allows you to delete a web page on the server. Again, browsers typically do not have the privileges to go and start deleting content on web server. So, most of the times you will not see a delete or a put happening, but the protocol actually has commands to support it. And then there is the head operation, which just gets you the header of the document, which is often used in caching. Okay. So if you have cached the web page, you can get the header of the web page to see if the web page has changed. If maybe if it has the last modified time in it, you can check. Okay, so that's how you would use the head request. But most browsers are going to essentially use get and post. Okay, so at the heart of it, HTTP is a very simple protocol. It will become very popular, of course, but very simple in design. Okay. Now, yes, question.
Which of these commands allow you to update a record that has already been created? So, for example, with post, you can fill a form and submit that information. Now, some record has been created at the server. Now, I want to update my information. So, do I use another post request?
Okay, question is, which command can you use to update information on the server? So if you post a form and it goes to the server, there's some data that you sent to the server. If you want to update it, how would you do it? So typically the way you are going to do any update, or even the initial one, is first you are going to do a get on the web page that returns the web page that has the form embedded in it. Okay. Then you fill the form, and when you submit, it goes as a post request. Subsequently, if you want to update it, you are going to send another get request to fetch that form. Typically, it might come back with some entries pre-filled, because maybe it's retrieved the previous entries that you already stored. Then you can again change the entries and submit it again. That will go back as a post. So it's a get and a post combination that you're going to use. Okay. Anything else here? Okay. So typical web interactions are between users who use browsers to connect to web servers, but that's not by any means all the types of communication HTTP allows you to do. There are lots of machine to machine or process to process communication that also uses HTTP. Okay, so that brings us to this topic of web services, where the two entities that are actually using HTTP to communicate don't involve humans at all. These are two applications that are communicating with one another. They are simply using the HTTP protocol to do so. Okay, so in this case, the server is going to expose an HTTP-like interface, and the client machine is going to use HTTP for communicating. Okay. The most simplest example of this is to use HTTP to perform what's called what we know as RPC. Okay, so essentially, you can use RPC that is tunneled over HTTP. You are making RPC requests using HTTP as your transport protocol, rather than just using vanilla sockets. Okay. So this is called web services. Okay, so you will have many different web services platform where you can essentially use client server RPC communication that goes over HTTP, and you will see familiar pictures here where the client has a stub. The client essentially has a runtime system that sends a request to the server has another stub to process the response, and so on. There's an interface definition language. In case of web services, that's called WSDL, web service definition language, that is used by the ideal compiler to auto generate the stubs and so on. Very similar workflow to what you have when you write RPC code. Okay, so now the initial standard used this complex protocol called SOAP, which is called Simple Object Access Protocol, to make RPC requests over HTTP. So what you would do is you would make a HTTP request. The entire RPC request was specified as an XML document that was sent as part of the HTTP request. Okay. The server will receive that XML document, it will parse it, it will extract the name of the method and the parameters, then it will perform the RPC command that is specified, produce a response that's also sent as an XML document back to the user. Okay, so here is an example of making a request. So you are essentially calling the alert method. Okay. You will see that as an HTTP URL, but you are calling the alert method, and then you are essentially sending a string, which is pick up someone at 2 p.m. as an argument to that method. And presumably the server will then call the alert method with that string and actually send an alert to whoever it is needs to be sent. Okay. That's an example of an RPC command that the client application has made to the server, and you will see that is encoded in a long XML document, which I won't go into, but that's what essentially XML looks like. Okay. That's an example of a SOAP request or a SOAP message, and you will get a response back similarly. Okay. And you will see that to make one call and send one string, you have sent such a large document that describes what this request is. So it's a complicated protocol. Okay. It has a lot of overheads, and didn't really work because there was too much overhead, it was far too slow. So what happened was SOAP evolved into what is called RESTful architecture, and you already used RESTful architectures in the class. So RESTful architectures also make RPC request over HTTP, as you probably realized. Your clients and server talk over REST APIs. You're essentially making RPC calls, just layering it over HTTP. You can send any request, you can send arguments and so on. And that is basically what this gives you. Okay, so in this case, our web service is more lightweight and it is point to point. Okay, the main difference between general SOAP requests and RESTful architectures is RESTful architectures assume one client, one server. SOAP assumes an arbitrary distributed application where many entities are communicating with one another. Okay, so in that case, you need a lot more complicated scenarios than if you are just making one client is making a request of one server. So it's point to point in some sense, which allows you to simplify a lot of things. Yes, question.
What does that mean when you said that SOAP assumes that there are arbitrary number of servers?
Okay, so question is, what does it mean when I said the SOAP requires arbitrary server? So SOAP is designed for an arbitrary distributed application where there are arbitrary number of nodes that are all communicating over RPC to implement a larger application. So you can have arbitrary communication that can go on, and each of this is essentially a SOAP interface between these two entities. Each edge says like this part of the application talks to that part of the application and so on. Okay? So SOAP is designed for the general distributed application scenarios. What RESTful web services do is what you assume in the web, where there's one client that's simply talking to one server and using essentially HTTP based REST requests. So this entire thing comes to basically two nodes that are just communicating with one another. Okay? That allows you to simplify a lot of different things because these entities might have state and you have to make some assumptions about what that state does to requests and so on. In RESTful architectures, basically you assume that there is no state. Everything you need to tell the server to perform your command is encoded in your HTTP REST request, and then you just send that over, it performs the request, sends you back a response, and then no state is necessarily maintained. Okay, so those assumptions make it a lot more lightweight. Okay, you're basically now doing point to point XML. I'm going to show some examples in just a moment, and it is layered on top of HTTP. SOAP uses HTTP but doesn't have to. SOAP can actually use non-TCP protocols and so on. SOAP doesn't even say you have to use HTTP or TCP more generally. Okay, but this one actually just uses HTTP. So here is an example of the same request, not the same request, it's basically a simple RESTful request where you want to essentially send a HTTP request to get the price of some stock. Okay, in this case, you want the current price of IBM. Okay, so you're going to do a get and say /stock price /IBM, send that off, and then you're going to essentially get a response, which does come as an XML document in case of this RESTful architecture. It can also come as a JSON object. Doesn't matter. REST doesn't say it has to be XML. These days you send back things as JSON, but originally RESTful architectures got responses as XML. Doesn't matter. You can define it any way you want. Okay, and then you have basically got a response saying here is the symbol and here is the price. Okay, so that's basically what has come back to you, and you can then process that and display it to the user. Yes, question?
So if the company's name is IBM Research, so if there's a space between IBM and research, then how do you send data in that case?
Okay, question is how do you send strings where there are space in them? You will use control characters to describe that there is a string. You will have backslash space and so on. That is basically part of the HTTP specification. How are you going to have a URL? Can the URL have a string and so on and so forth? Okay. Any other questions? So you have percentage control characters that represent space that can be represented this way. Yeah, so here is the same call that is made using SOAP, and you will see that you are basically asking for stock price of IBM, but you have sent a complex SOAP XML request and gotten a complex, not very much more so, but still a complex SOAP response. Okay, in the previous case, all of that basically went through your URL itself. Okay, you basically specified the method you want to call and the arguments possibly using HTTP URL. Here you are using HTTP as your transport, but all the method name and the commands are actually sent as an XML document, which makes it more complicated to process.
Is there a limit to the length of that? IPv3 character document?
Is there a length of the XML document?
No, like for example, IPM is like 3-letter long. Is there a length, number of characters length?
Well, the question is there any limit on the length character? There shouldn't be any such limit. You can specify whatever method name you want, whatever arguments you want in there. Okay. Yes.
So it seems like this XML is just like a way of serializing like that call to the method, right?
XML is the way to do serialization. Yes.
So if it was okay to do that in like RPCs, why is it a problem here? Like
You are asking why is it a problem to do serialization?
I mean, you said that the reason why this didn't catch on was because these documents are very big for like small requests.
Right.
But then, why is that a problem? Let me.
So the question is why is this a problem? So it all comes down to efficiency. Okay, there is nothing wrong with using this, but to actually just figure out that you are calling that method and this argument, you have to first use an XML parser, parse this document, get the document encoding, then figure out, walk that document and get the parameters and the method name. Okay. In RPCs, you would have actually sent in your request just the method name and an argument. Okay. If there's a complex data structure, you will serialize it, of course, but I mean that's going to happen even here. But this requires a lot more overhead to process, and if you want to deal with efficiency, then you want to reduce that processing overhead. And the point is RESTful architectures is anyway you have to process your URL. So if you encode information in the URL, then you are already getting all the information you need. There is no need to go and process the body on top of that. It saves on some processing overhead. Okay. All right. So that's the SOAP call, which we will ignore here. Okay. Here is the difference between set of differences between SOAP and REST. Okay. SOAP is language, platform and transport agnostic. You can write SOAP applications in many languages. Okay. It runs on many different platforms and it does not have to use HTTP, although that was a common way to run SOAP based application. Okay. And RESTful architectures are the same. You can write RESTful applications in whatever language you want, Python, Ruby, PHP, doesn't matter. So that is the case, but it's not transport agnostic. It uses HTTP. Okay, that's the default. Okay, this supports general distributed computing, which was basically what I showed here. Your arbitrary set of intercommunicating applications. This uses point to point. A client makes a request to a server. One application makes a request to another applications. No intermediaries. Okay. There are a whole set of standards were developed by the World Wide Web Consortium to write RESTful applications. SOAP application. Okay, here there are no standards at all. You just write, so long as you have a interface that is RESTful, you can write it any way you want and it's still considered to be RESTful, because what is inside doesn't matter. What's the interface you expose is what matters in this case. Okay. How you write the application is not of concern to people who are going down that path. Here, how you write the application matters. You have to write an interface definition language, use the standard compilers to compile it, generate stub code, and so on and so forth. Okay. There's more error handling, this extensible, heavyweight, and harder to write and whatnot. This is simpler because if you know how to write HTTP applications, it's easier to pick up. Okay. Tied to HTTP, it's somewhat concise in the request format and the responses and so on. Okay. So those were the key differences, and needless to say, this is what actually happens today by most applications that you see on the web that expose any interface at all will expose RESTful interfaces. Okay, and then they are used by other applications, not necessarily web browsers, to communicate, fetch data, and so on and so forth. There is a common way to write RPC applications over the web. Yes, question. Yes. So question is if you have the general distributed architecture, can you actually process, have one server receive a request, another one receive a response? So you can build your application any way you want, just as you write distributed application in any other programming language, the mode of interaction does not matter, that what the application does is actually what matters. The only thing that is important here is every entity in your system is going to use SOAP. Right? So, let me give a much more concrete example. So, in your lab, essentially you had a RESTful interface to the web to the clients, but then we said if it is a multi-tier application, you can use any interface internally between the front end and the back end tier. It did not matter. That did not have to be RESTful, it could be anything. If you write this in SOAP, every interaction will be SOAP. You will have a client sending a SOAP message to the front end server, that is going to send a SOAP request to your database tier, everything just uses the same language. Here only the interface is RESTful, what happens internally is not important. Okay, so that's I think that may kind of differences. So the answer to your question is yes, you can have any interaction you want in your distributed application. The response can come from some other server. That's fine. Okay. All right. So that is SOAP. Now we'll talk about web proxy caching. So again, in this case, we are switching gears from SOAP and RESTful architectures to caching. Okay, so now the picture that you want to keep in mind for the rest of the lecture is you have now a client, a server, but there's a proxy sitting in between that's going to intercept requests and send back responses. Okay. And we'll assume not that there's one proxy, but there could be a collection of proxy caches that sit in between. Okay. So in many cases, these proxy caches can communicate with one another, not just communicate with the server. Okay. So there is this concept of what is called cooperative caching, where the caches actually talk to one another, and that's the example shown here, where you have a client that sent a request to the web proxy. Okay. The web proxy is first going to look in its local cache for the requested web page. Okay. If it's a hit, you are done, you just send that response back. If it's a cache miss, then typically you would have to go to the web server, okay, and fetch that document. However, if the caches cooperate with one another and this cache finds that there's another cache nearby, it might actually be faster to ask that cache if it has the document and retrieve it before you go to the server. So for example, maybe you put a cache in this building and then another cache may be in the EC department. So if this cache has a miss, you can go to another cache nearby and try to fetch that document, or going off to some remote server on the internet. Okay. This is called cooperative caching, where the proxies have this caches in them, and they basically look like one large logical cache. If it's not in your local cache, it might be in a nearby remote cache. Okay. This allows you to improve your cache hit ratio, because every time there's a miss, maybe you don't have it locally, but somebody else has retrieved that document from another cache nearby. Okay. So we are going to use this concept in just a little bit. So keep that in mind. Okay, this is just called cooperative caching. Okay. But the more important thing for us is to also deal with the notion of consistency. Okay, now whenever a browser goes to the web server and fetches a page, you are guaranteed that the page that's come to you is what is the most recent version of the page at the server. Okay. Now if the page is coming to you from a proxy cache, how should the proxy ensure that the content in its cache is consistent with the content at the server? If the web page actually changes at the server, how should the cache know that the web page has changed? If a request for that web page comes in, and if you just return what is cached locally, you might be serving an old version of the web page. That's never going to happen if you go directly to the server. Okay. So you have to ensure consistency of your cached web pages. And the question is, how are you going to go about doing that? Okay. Is that clear what we are going to talk about? Okay. So consistency issues are basically say web pages tend to change over time. Okay. Some web pages are static, some are dynamic. Okay. Dynamic web pages are those that are generated on the fly based on the request. You never tend to cache dynamic content, because every time the web page might change, you are just generating it based on a program. But static web pages, which are HTML pages or static images that you store on disk, you can certainly cache, but they can change from time to time, and the question is, what do you do if they change? Okay. Now the problem that you will face in this case is that different web pages will have different popularities and they will have different update frequencies. Okay. They are two different things. Popularity is how many times is this web page requested by users. Okay, what's the request rate for this one web page. Okay. Update frequency says how frequently is this web page changing. Okay, that's the update rate. So maybe if you are front page of a very popular news site, your web page might change every few minutes because you might have breaking news sections or real-time updates that are taking place. So every minute, few minutes, your web page is changing. Okay, that's the update rate. Okay, and then depending on how popular this web page is, you have the request rate as well. So you want to deal with both how popular is this page and how frequently is it changing to decide how to cache that content at different caches and still deliver the freshest content to the user. Okay. We will talk about two different methods to do this. One is a client pull based consistency. The other is a server push based consistency. Okay, so you can use push or pull to ensure consistency of your request. Okay, the second thing you can use is whenever the web page changes, either you can cache can get notified that the page has changed, in which case it will discard the cached page, or you can get an update, which means you will say the web page has changed and here is the new version. So you actually got the content in addition to being told that the web page has changed. Okay, so that's basically this invalidate versus update. Okay, so you will have to discuss when do you use push versus pull, when do you use invalidates versus updates, and so on. Okay, so let's start with the first approach, which is server push based approach. Okay. In your server push approach, it's the job of the server, web server in this case, to keep track of every proxy that has requested a page. Okay, so you will keep track saying, let's say index.html, you will have a list saying the following proxies have a cached copy of this web page with their IP addresses and so on. Okay. Whenever that web page changes on the server will look up its list and send either a notification saying this web page changed, or you will send the new copy of that web page saying here is the new version of this page. Okay. So if the web page is modified, notify each proxy. Notification times is either indicate the object has changed, so you are sending invalidated messages, okay, not the actual page, just the fact that it has changed, or you are going to send new version of the web page, which means you are sending an update so that the cache can actually replace what is there with the new one. Okay. Now you can decide when to send invalidate or when to send update. So maybe if the web page is popular, it makes sense to send an update rather than an invalidate, because popular web page essentially means the proxies are receiving lots of requests for that page. So if you send a notification, very soon somebody is going to request that page and this proxy has to ask that server anyway. So you may as well just send the web page and say here's the new version, it changed. So you don't have to have the proxy ask you again. Okay. On the other hand, if the web page is not popular, okay, less popular page, and some proxy caches it, maybe you send a notification saying the page has changed rather than the entire page. Okay. It goes without saying that notifications or of invalidates are smaller messages than updates. So this is more efficient to send than that, okay, because the object could be of arbitrary size. Notification just says this web page changed, it's a small message. Okay, so sending updates is going to be a lot more expensive, and you only want to do it if the web page is actually going to get access at the cache. It's popular at the cache. Is that clear? Yes? Okay. So the question is, what happens if there's an invalidate? So a proxy has cached a web page. Okay, the web page got updated at the server. Server sent an invalidate to the proxy. Once you get an invalidate, you delete that page from your cache because it's no longer valid. So now when a next request comes in, you will have a cache miss because you no longer have that page. You go back to the server and fetch it. Okay, that's what is going to happen. If you had an update, then you basically have already sent the new version. So you delete the old and you put the new. So the next request will still result in a hit, not in a miss. Okay, the question is.
I'm not seeing like a particular advantage in this caching mechanism, because like the number of requests that are like happening between the servers is much more than, let's say you replicate a web server itself. Like if the concern is that the load on the web server is.
So what's your question again? You don't see the benefit of web caching? Is that what you're asking? Or
yes, because like the number of requests, like because like if one front-end server, it has to query the rest of the servers probably within its list. Like, do you have a cached copy of this? Do you have a cached copy of this? So
hold on. So, are you asking question about cooperative caching, or are you asking question about, okay, we have not come to cooperative caching. Right now we are assuming one proxy cache. Okay, we will generalize to cooperative caching in a moment. So, we are just assuming this model where there is one browser, not one browser, many browsers, but one proxy cache, one web server. So, if there are other proxies, they do not talk to one another at this point. Okay, we will come and talk about what you just said in just a moment. So, this is simply asking this question. This proxy is not going to ask anything else. If there is a miss, you go to the server. But we will come to your question in just 2 slides or so. Okay. So, pull based approach. So, let us talk about push based advantages, disadvantages, then we go to pull based. So, advantages of this push based is you give tight consistency guarantees. Every time a web page changes on the server knows about it, obviously, because you are changing it at the server. You can immediately send consistency messages to proxy caches. Okay, so, you get good consistency guarantees. There is not going to be a whole lot of stale data, because you only have to wait for these messages to propagate to the server. Proxies can be passive. There is no intelligence at the proxies. All the state is kept at the server. Okay. Disadvantages, this makes HTTP a stateful protocol. Okay. HTTP by design is a stateless protocol. Now, for every web page, you have to keep track of all the proxies that cache it. So, now you have actually state for a web page that says who else actually has a content, and every time there is an update, you have to propagate an update or send notification. Okay, so, this basically makes HTTP stateful. Okay. The other problem is state might have to be kept indefinitely. How long should you keep track of this list of proxies, okay, and keep sending them notification? Should you do it for a day, week, month? There is no limit, because you are just keeping state. If the proxy wants just to cache a page for 6 months, you will have to keep sending notifications. Okay, so, in other words, if there are lots of proxy caches that cache a web page, the state can be large. It might have to be kept for long periods of time. Okay, so, that is a disadvantage of a push based approach. So, if the server crashes and all of the state was stored in memory, then you are going to lose it. So, if you keep it on disk, you will not, but if it is a memory state, you are going to lose that state. Okay, so, pull based approaches, everything is now the opposite. So, now it is the job of the proxy to keep track of consistency. Okay. The way you are going to do this is you are going to poll the server. You are going to poll the server and ask, has the web page changed? Okay, and if the server will tell you it has changed, you can fetch a new version of that web page. Okay, so, proxy periodically polls the server to see if the web page has changed, and the way you can do this is HTTP has something called a conditional get. Okay, the get request that I showed you for the HTTP has many different flavors. Okay, the typical get is just get me the page, but you can basically specify an if condition for the get. The if condition, in this case, you can say if modified since, and you can specify a date and a time, saying get me this URL if it has been modified since this date and time, since it is modified since 11 a.m. this morning. So, if there is a change since that point, only then you will get the web page, otherwise the server will say not modified. Okay. So, how do the caches use this? Whenever you fetch a web page and put it in your cache, you store a timestamp of when you fetched it. The next time you want to poll the server, you are going to send a if modified since get request, and you will specify I fetched this web page at 11 a.m. get me this web page if it has changed since 11 a.m. If so, you will basically get a new copy, otherwise it will say not modified. Okay. So, this can be purely used, purely supported through HTTP. You do not need any new protocol. For server push, there is no HTTP mechanism to do it. You have to do it by your own protocol. But client pull, you can essentially use HTTP requests itself to support consistency in your cache. Okay. So, you can use if modified since HTTP messages to poll, but then the question is how frequently would you poll the server? Okay. It should be clear that if a web page changes at the server, okay, the proxy has no way to magically know the web page has changed. The only way it is going to know is the next time it polls. Until then, you have an old copy of your web page. If you send a request comes in and you get a hit, you are actually serving old content. Okay, only the next time you poll, you will even figure out this web page has changed. Okay, so, what would you do? How frequently would you poll? Okay. So, you could say let us poll frequently, let us poll once a minute or something. So, you can pick whatever period you want. Okay. But you will realize quickly that that is going to be highly wasteful. If some web page changes once every 3 days and you are polling once a minute, you are sending a lot of requests every time the response has a document not changed, and you will just keep polling the server and just telling it does not change. Okay. So, if you have not very frequently updated content, frequent polling is extremely wasteful. In server push, there is no wasteful messages. Okay, you just wait for the server to tell you. It does not matter how frequently it changes. Every time it changes, it sends one message. Okay, that is optimal. Okay, in client pool, unless you know how frequently it changes, if you basically poll it more frequently than that, you are going to waste messages. Okay. But on the other hand, if you say I won't poll frequently because there is too many messages, you have the risk of out of date content. Okay, if you say I am going to poll once an hour and the page changes much more frequently than that, then for an whole hour you have old content and then you do not know what the new content is until you poll it the next time. Okay. So, in some way the polling frequency has to be tailored to how frequently the object is changing. There are two ways to do this. Okay. One is you tell the server to specify an expiration time on the page. Okay. This is called a time to live value. So, as part of your HTTP response, you can get an expiration time. Okay. Now, an expiration time can be assigned by the server as some estimate of when the web page is going to change next. Okay. Clearly, the server cannot know when the web page is going to change next. Okay. How is the server going to know when you as a user is going to make your next blog post? It has no idea. It can only guess, say you seem to make updates once every 3 hours. So, it can set an expiration time based on past history, but there is still no guarantee. Okay. It is just an estimate from the server, but if the server gives you an estimate, the proxy can say I am going to use the expiration time, and when that time expires, that is when I am going to poll next. Okay. If the server may gives you a good expiration time, you are going to not waste any messages and you are not going to have outdated content. But as I said, that is only an estimate. There is no requirement that because the server has given an expiration time, the user cannot change his or her web page at the server. Okay, so, you can still get outdated content because of this. Okay, but it is one way you can actually let the proxy figure out when to poll next. Okay. The other way is let the proxy has some intelligence that allows it to dynamically figure out how frequently a web page is changing. Okay. So, in this case, you can dynamically change the polling frequency based on what you are observing. Okay, so, here is one approach. There are many such approaches. So, you can use past observation. So, let us say first time you send a web page, you set a very small poll interval. So, you poll after the 1 minute. Okay. If the web page has not changed, then you say I am going to increase the duration and I am going to next poll is going to happen after 2 minutes. So, then you poll after 2 minutes. If it does not change, then you say I will exponentially increase it to 4 or whatever the number is. So, you keep increasing the poll duration until you find that the web page has changed. Okay. So, that has allowed you to discover the time between you fetch the web page and when it changed next. Okay. So, you can use that as an estimate to guess what the next poll duration should be, and you can then figure that out. Okay. If you find that you polled and the web page has changed since you can actually reduce the polling frequency to discover how frequently the web page is changing. So, you are varying your poll duration based on what observations you make of how frequently the web page changes. So, for frequently changing web pages, you will basically poll after 1 or 2 minutes, you will see the web page has changed. You won't increase the poll duration beyond that. You will say I am going to poll frequently because it looks like the page is changing frequently. For infrequently changing web pages, the poll duration will keep increasing because you do not find it has changed, and then you will basically use a longer poll duration. And if suddenly the web page starts getting updated more frequently, you will change it back, because every time you get an update, you will basically reset and start from a small poll duration. Okay. So, this is adaptive polling. Okay. It requires no knowledge of the object characteristic. You do not know how frequently the web page is changing. You are dynamically discovering by probing. Okay. And then based on what the probes tell you, you set your poll frequency. So, in this way you can use client poll, which is intelligent enough to figure out what the web page changes. It requires no server support. Okay, if the server gives you no time to live values or gives you incorrect, doesn't matter, you can still figure out what to do. Okay, is that clear? Okay, so that is intelligent polling using client pull messages. Here are some advantages and disadvantages. The main advantage is you don't need any extra protocol to implement this. You can just use HTTP messages and conditional get messages, which are called if modified since or IMS messages. Okay. IMS gets basically mean if modified since get. Server remains stateless. Okay, still HTTP server doesn't have any state of what who's cached what. The client proxies, not client. The proxies are actually asking the server whether the page has changed. So it's resilient to failures of servers, obviously. Okay, it gives you weaker consistency guarantees because there's never a guarantee that the web page hasn't changed between two successive polls. Okay, and for a little bit of time you're going to have out of date content. Okay, so it's not as strong. Okay. The only way you're going to get stronger consistency in client pull is every time a request comes in, then you first query the server using an IMS get and ask if it has changed before you send a response. Okay. But if you do that, you're defeating the whole purpose of caching. Okay. The whole point was you will get lower latency because you don't have to go to the server. You have cached it locally. If every request requires you to ask the server, okay, you will never serve stale content, but you are not going to get benefits of caching either because the latency to check with the server will actually add to the total latency to respond. Okay. This requires more sophisticated proxies, and clearly the message overhead is higher than server push, where you have one message going from the server to the client every time there's an update. Here, depending on how many polls you make, you might have more than one, lot more in many cases. Okay. All right. So that is pull based. So now I'll talk about a hybrid approach that combines some advantages of push and pull based approaches. Okay. The push based approaches give stronger consistency guarantees, but it also made the server stateful. Okay. The pull based approaches put all the burden on the client, but then you got weaker consistency guarantees. So can you combine both of those things together? Okay. We are going to talk about this technique called leases. Okay. This is a general technique in distributed system. Okay. We are going to see it only once during the course, which is in this context. Okay, but it is used in many different scenarios. Okay, so first, let's ask what do you mean by a lease? Okay. Just as you sign a lease to rent an apartment, which is a contract between you and the landlord to have maybe your apartment for a certain period of time in return for some rent. A lease is a contract between two entities, two parts of a distributed system. Okay. And in this case, the lease is the duration of time, specifically the lease duration is the time for which the server agrees to notify the proxy if the web page has changed. Okay. So if you basically say, give me a 1 hour lease, and the server says fine, that means for the next hour, if the web page changes, you will get a push based notification. Okay. Once the lease expires, then the server stops sending you notifications. Then it's up to the proxy to say, should it renew the lease, should it let it go and wait for some more time before it renews the lease. That's up to the proxy. Okay. So that's essentially what is shown here, where the client sends a read or a get request to the proxy. The proxy basically it's a miss initially. You get a request and ask for a lease. The server says, here's a web page, here's a lease for this duration, and until that time expires, you are going to get invalidates or updates pushed from the server. Okay, but the time for which the server is obligated to do this is limited by the duration of the lease. Okay, you don't have to, unlike server push, you don't have to keep this state indefinitely. Once the lease expires, the server can delete that proxy information from its state. Okay. So you issue a lease on the first request, send notification until expiry, and then it's up to the proxy to figure out if it should renew. If the web page is popular, you should renew the lease because there are requests coming, you want to keep caching that object. There are no requests coming for this web page, then there's no need to renew the lease because why should the server send notification for a web page that nobody is accessing? Okay, so the proxy can intelligently decide when to renew the lease as well. Okay. Now you will see the reason this is a hybrid is depending on the duration of the lease, this starts looking like client pull or server push. Okay. In particular, if you set the lease duration to infinity, okay, this becomes the same as a pure server push, because you made a request and then the server is obligated to keep sending you notification for arbitrary period of time, same as server push. If the least duration is 0, this is same as client pull, because you retrieve a request and then there is no more notifications coming. So you have to basically send the next request as a pull. Okay, so anything in between is basically going to be an hybrid bit that looks more like server push or client pull, depending on is the least duration closer to 0 or is it very large. Is that clear? Okay. So the efficiency of this approach obviously going to depend on least duration. You can say, how do you decide the duration of the lease? How does the server decide that? That could be based on the age of the object, which means how frequently is it changing. It can be based on popularity of the object, which means how frequently is it being accessed. It could be based on the load. If the load on the server is high, you can reduce the lease durations and start deleting the state faster, because you have high load, so you cannot send lots of notification. So you start timing out leases faster. Maybe at low load, you can keep state for longer. If the object changes very frequently, maybe you should give longer leases. Or if it's more popular, you should give it longer leases, because the notifications you send to the proxies are useful. Proxies are actually seeing lots of requests for this server. Okay, so these are different policies. How the server decides is based on the situation. Yes, question.
In the entire internet, if there's a server which is like serving some content, and if there's a proxy, then who owns the proxy?
Okay, question is, if there is in the internet, if you have proxies, who owns the proxy? So that depends on the scenario. It is entirely possible to get open source proxy, and you can run your own proxy in your home network and point your browser. In most cases, we will see that proxies are run by content distribution networks that have deployed a global set of proxies everywhere. And they are essentially providing a service to the users on behalf of the content providers. So in this case, there are companies that go and deploy these proxies as a service to the end user. Okay? So when we talk about CDNs, maybe not today, we are running out of time, we will talk about them. Okay? So I am going to show in the 2 minutes a simple example of cooperative caching. So we talked about server push, client pull. Maybe the question, yes.
Does the server have to provide the exact duration of lease as the proxy request?
What's your question again?
Suppose proxy request for 1 hour lease, does the server have to guarantee that he will provide a 1 hour lease?
Okay, question is, if the client proxy, not the client, the proxy requests a lease of a certain duration, should you provide that? The general assumption is there are 2 ways you can do this. Proxy can just say, give me a lease, and the server can decide what the duration of the lease is. In that case, it's the server's job to figure out. Okay, you can also ask for a lease of a certain duration, but then the proxy has to figure that out based on some metric. It's often better for the server to figure that out. Okay, so the assumption here is the server is deciding on the lease duration, but you could have proxy figuring it out based on its statistics of how long it wants, and then the server can decide whether to give it. Okay, but this one just assume the server decided. Okay, so we have 1 minute left. I'm going to show a picture. Okay, so whether you use client push or server push, client pull rather, client pull or server push architectures, you can also have proxies talk to one another, and that was the picture I showed earlier, and there was a question about why does it matter. So it matters when you have large numbers of proxies that are basically doing content distribution. Here's a quick animation I'm going to show where you have 3 caches at the leaf. Okay, this is a hierarchy of caches. There's one parent cache. So there are 4 proxies here. That's the server, and these are your clients. Okay, so I'm going to show you, and there is some open source versions of this like Squid that you can download, and you can set up this hierarchy, or you can set it up as a standalone cache as well. So maybe you get a request, it goes to that proxy. Okay, maybe it's a cache miss. If it's a cache miss, then that proxy is going to ask its leaf, its peers and its parent, saying, do you have this object? Okay. ICP stands for Internet Cache Protocol. That's a protocol that allows one cache to talk to another cache using cooperative caching. Okay. So now if either of these 2 nodes have it, then they are going to return that object. If they don't have it, then the parent is going to recurse. Okay. If this is a multi-level hierarchy, the parent would have sent it to its parent and its leaf nodes. But in this case, there's only parent is the root. So we are going to assume that no one has it. In that case, the the HTTP request sent to the parent, and this is going to recurse. Okay, so parent will get it from the server, then it's going to come back down, and then you get the response. Okay, so now notice that to serve one HTTP request, how many messages have gotten exchanged here. Okay, so the browser and the user is just waiting. Okay, and these proxies are all communicating, and the request is trickling up. So whenever you have a miss, this kind of architecture, unless you can get the content quickly, is going to get you very bad performance. Okay, but if there was a local hit or some web that page was cached nearby, this would be very good. You would basically get it much faster than going to the server directly. But if you are unlucky and you get a web page that no one has accessed anywhere in your cache hierarchy, then you are going to wait for a long time. Okay, and next time I'll show you a different architecture that's going to do cooperative caching but avoid some of these problems. Okay, but let's stop here for today.